Hi, welcome to es301 Engineering Analysis. This is chapter 11 on Gauss-Seidel. So here are the learning goals. At the end of this video, you will know what a banded matrix is and what engineering problems lead to banded matrices. You'll understand what the Thomas solution algorithm is. You'll know what Cholesky decomposition is and how to implement it for a banded matrix. You'll understand when the Gauss-Seidel method may be a preferred numerical technique, and you'll be able to implement the iterative Gauss-Seidel method. So first I want to review what is a banded matrix. Here's a diagram from the textbook. And so remember, we're dealing with matrices, and these matrices are almost always square when we're solving numerical problems. A banded matrix has these triangular regions that are full of zeros. So those are all zero elements, and the only non-zero elements occur along a diagonal. And so first there's going to be a diagonal one element wide that might have some values in here. And then there's going to be maybe one or two or three, some number of elements off to the side. Usually these matrices are very large. They could be, hundreds or thousands of rows and columns across. And usually the bandwidth is a very small fraction of that. When we talk about the bandwidth, we're talking about the total number of columns on a single row that are non-zero. That's the full bandwidth. Bandwidth will always be an odd number because this light blue region over here will always be the same width as the other light blue region, and that's called the half bandwidth. So therefore, if I take the half bandwidth and add 1 to it right over here, and then add another half bandwidth, I would get the full bandwidth. So the bandwidth is 2 half bandwidths plus 1. Right? So that's what a banded matrix is. And they often arise pretty common in engineering problems. And so I want to come back to a problem we've mentioned before that results in a banded matrix here, like this. So imagine I have some sort of rod, maybe a steel rod here. It's hot on one end, and it's cool on the other end. And so I want to go ahead and find out, for example, what the temperature distribution is in here. I'm going to do that numerically. And so what I'm going to do is I'm going to go ahead and discretize this rod. And I'll just do it in one dimension, assuming this rod is very long relative to its lateral dimensions. And so I'm going to have some number of discretized points over here. And so, for example, that point right there I might call the temperature at node I. And so then this temperature over here, this will be the temperature at I minus 1. That one right there will be the temperature at I plus 1, etc., etc. As I showed in a previous video, if I want to go ahead and numerically approximate the second order derivative of this, so I want d squared t, d, let's call it the x direction, d squared t dx squared equals 0, steady state temperature. The temperature at some particular, to go ahead and implement this equation, I can go ahead and express that in terms of the temperature T sub I and the two temperatures next to it. In fact, that equation was T at I minus 1 plus T at I plus 1 minus 2 times T at I is equal to 0. So right there was the numerical approximation of that. And so this was one of many, many simultaneous equations. But notice this equation right over here, which would be occurring at row I, for this element here, it only depends on the two temperatures next to it. And so if I kind of look at this at a sort of a banded matrix idea, you can kind of see what I end up with. It would look like this, where I've got my matrix A here. So here's my temperature T sub I. And so this right over here would be the minus 2. This would be the positive 1 and the positive 1. And then I have all these zeros on the side. So if this was a really, really long rod, I had very, very many elements across it, I could have a very, very large square matrix, but a fairly narrow band right over here through here. So this often arises in engineering problems where you have these banded matrices. And so it would be kind of nice if there were solution techniques that could take advantage of the fact that you've got this huge number of zeros over on these sides here. All right, so first I want to talk about a couple algorithms before I get to Gauss-Seidel. First I want to mention is the Thomas algorithm. And the Thomas algorithm, it is simply LU decomposition for a matrix where we've got the bandwidth of 3. So that means I have a diagonal band, and I've got a half bandwidth of only equal to 1. And so I can look at the matrix this way, and so what's often done, here are all of my zeros, is that since I know I'm only going to have 3 when I implement the Thomas algorithm, it's usually given the letters E, F, and G for what these 3 lines are across here, these 3 diagonal lines have right over there. And I can go ahead and just implement normal LU decomposition, which is back substitution and forward substitution. So you first start off with the decomposition, where I'm going to go ahead and start modifying this value E here. I start at the second row because I'm not going to change the first row. I go ahead and modify what my values of E and F are. And so then that's all my looping only begins at 2. Then I do the forward substitution where I'm dealing with the B matrix, or the right-hand matrix is what the notation is here. That's why it's using R. And then I do back substitution starting at the bottom to go ahead and solve for what my values of X are. So Thomas algorithm is just LU decomposition like we saw in the previous video. In fact, if you have a algorithm for LU decomposition, you can go ahead and do the Thomas algorithm. You can go ahead and solve this matrix. If you know it's only going to have 3 lines, you can make it a little bit more efficient instead of looping through all of these 0 values. And so that's kind of the primary difference between the Thomas and LU. It's just a specialized form of LU decomposition. I want to talk about next about a different one, which is called the Cholesky decomposition. And so what Cholesky does is we take our matrix A, and we're going to go ahead and find some matrix L such that L times L transpose is equal to A. So we need to figure out what L is. Remember, transpose just means I go ahead and flip it horizontally and vertically, so the thing in the lower left becomes up in the upper right. And so if I was to go ahead and look at, for example, the Cholesky matrix, for example, let's go ahead and just kind of sketch one up over here. What I would do is I'd have some elements down the diagonal. I'm going to go ahead and call them L. So this would be L11, L22, L33, L44, etc. as I go down. And then what I'd do is I'd have some elements down here. This would be, for example, L21. And there's going to be this down here. And L21 is going to be the same element as up here. So L12 is L21. I can just go ahead and call it L21. So these two elements are the same. There's going to be an element here. It's going to be the same as the one there. Element here is the same as the one there. So I'm just kind of flipping it horizontally and vertically. And they share the elements right over here along the diagonal. Right? So that's what Cholesky decomposition is. And you might wonder, why would you go to the effort of finding this particular vector L or matrix L for it? And the reason is that first of all, since the elements in the upper right are the same as the lower left, you actually only need to store more or less half the matrix, plus some more extra elements along the diagonal. So in terms of storage, it can be more efficient, which again matters a lot if you're solving huge numerical problems where memory becomes an issue. Another thing that's interesting is that the symmetry, the fact that you have the elements 2, 1 equal to 1, 2, etc., often naturally already arises in engineering problems. In fact, if we look at that heat transfer problem we discussed a minute ago, what you'll find in problems like that is that you already have this symmetric matrix where you've already got A actually turns out to already be equal to L, and you don't even need to do the decomposition in the first place. Now, one of the things is the matrix must be positive definite. And what positive definite means is the elements down the middle right over here have to be positive, and they have to be the largest element that you've got in there. So you need to make sure that it's positive definite. Otherwise, when you go back and try to solve Cholesky decomposition, you're not going to be able to find a solution for it. Okay, so there's some reasons why you might go ahead and use Cholesky decomposition. And let me just mention what you would end up doing, right? Let's just kind of look at what we're trying to solve is AX is equal to B. And now if we do our Cholesky decomposition, we find this matrix L. So what this ends up being is L times L transpose, because that's what A is, times X is equal to B. And now we know what L is. So what I'm going to do is I'm going to define this L transpose times X as a matrix C, an intermediate matrix. So what you see now is you've got two equations. You've got L times the matrix C is equal to B. And then I've got just defined that L transpose times X is equal to C. And since these L and L transpose are these triangular matrices, kind of if I was just to draw a picture, it look like this is like what L is. I'm multiplying that by C to go ahead and get B. And then I've got my L transpose right over here, which is going to be times X is equal to C. And you realize I can do one by forward substitution and one by backward substitution fairly directly because they're these triangular type matrices. You've only got elements here, and you have zeros in the corners right over there. Once you go ahead and if you want to determine what your values of L are, there's kind of a simple algorithm shown in the book, and so I just kind of reproduce it here, but you've got it in the book. If you want to find the element L of Ki, it's using L for Cholesky. So it's an element of the L matrix there. This is how you find your off diagonals, and then this is a different equation for the diagonal. So find them right down the middle, 1, 1, 2, 2, 3, 3, etc. I go ahead and use that lower equation right there. Let's just go ahead and just kind of look at a quick example here. And so let's imagine I want to go ahead and find the Cholesky decomposition of this matrix this matrix A that I have right up here. And so remember, what I'm doing is I'm finding a matrix L, which would have, this is going to be a 3 by 3, so it would be L11, L22, L33, going down the diagonal. And then this element over here I'll call L21, it would be L31 and L32. And remember that if I multiply it by the transpose, so it's got the same diagonals, L11, L22, and L33. 2,1 goes right up here, and 3,1 goes right up there, and so my value 3,2 goes right over there. So this is this is L, this right over there is L transpose, and that whole thing right there is going to be equal to my A matrix that I have in the upper left. So for example, there's going to be a number 3 in there. And so if I want to go ahead and determine, I can go ahead and look at, let's go ahead and take this first row and then multiply it by that first column. We know that equals to 3. What that says is L11 times L11, and then there's just a bunch of zeros. And so that all is going to be equal to 3, or effectively what is A11. And so what I realized is L11 is just the square root of A11. And that was that first algorithm we saw for diagonal elements. And you can go ahead and just kind of keep doing this through a recursion. There's going to be more iterations each time, but if you program it, it's pretty straightforward. So that's how you go ahead and implement Cholesky decomposition. If you do it on this matrix right over here, if you want to do it yourself and verify, you end up with this matrix here. Remember, those elements, this is symmetric, so those elements are going to be going right over there. You can also do this in MATLAB. Not surprising, there's a function called CHOL for Cholesky. And so if I just said CHOL of A, it would go ahead and return that matrix right there. And so remember, you need to make sure that these things are positive definite in order to implement that function. All right, so finally we're going to get down to Gauss-Seidel. And so I first want to go ahead and talk about what is Gauss-Seidel, and it's another way to go ahead and solve the simultaneous equations, these matrices. It's often done with banded matrices. And so what we'll see, when we have really, really large matrices, remember, when we're going ahead and doing our elimination steps at the beginning, the elements in the bottom of the matrix keep getting multiplied by very many values each time. And so if you've got any sort of round off there, it's going to compound. And after a while, you could end up with the bottom equations near the bottom of that matrix being somewhat inaccurate. So that's not going to lead to a very good accurate solution. And so as I say here, then it can become more accurate to trade off the efficiency with accuracy by using Gauss-Seidel. And so what Gauss-Seidel does is effectively we don't precondition the matrix, meaning we don't do this elimination step at all to end up with these nice pretty LUD kind of decomposition type matrices. But instead, we're just going to go ahead and start with A right away, and we're going to guess a solution for X. And then what we're going to do is we're going to iterate through. We're going to keep modifying our value of X, but we're never going to change A. So we're not going to have to worry about any modifications due to round off error that I have. Okay. So for example, what I would do, so let's go ahead and imagine we were solving this matrix we just did with Cholesky decomposition, but instead we'll use Gauss-Seidel. What we would do is we're not going to modify the matrix A at all. What we're going to do is we're going to guess values for X. So we're going to guess values for X1, X2, and X3, plug it in, and then go ahead and modify those values of X each time. And actually, to keep this fairly simple, we're just going to initially guess that every X sub I is initially 0. So it makes it pretty simple. So let's go ahead and look what I do in our first iteration. I'm going to take my first equation, which says 3x1 minus x2 plus x3, and that right there would be equal to 5. And I'm going to use that to solve for x1 using my current guesses for every other x, x2 and x3, which we guess are 0. And so if I go ahead and do that, what I realize is I end up with a new value for what x1 is, and x1 is going to end up being simply 5/3. And so there's my new value of x1, and then I'm going to use my second equation to go ahead and solve for x2. So you can kind of think of it as I've got this vector of x1, x2, x3, x4. I first fill in all zeros. I use the first set of equations to go ahead and solve for a value of x1. Then I come down x2. All the things below it are 0, but now I've got a value for x1. I'm going to go ahead and move through, then loop back again, loop through, go back again, and then hopefully this is going to go ahead and converge, and those values of x, are going to be changing each time. Here I'm going to go ahead and use my normal definition of approximate error, where I've got what my value of x is at my current guess minus what it is at the previous guess normalized by its current guess. And what that means, I'm going to have a value of epsilon a for each value of x in here. And so my stopping criterion might be that every single one of those has to be below some particular criterion. Maybe every one of these errors has to be less than 0.1%. So I would evaluate an approximate error for each individual value of x. Right, so I want to first kind of mention convergence, and then we'll do an example. As often happens with iterative techniques, they can be non-convergent. And Gauss-Seidel, turns out, is non-convergent, and it's a similar way to fixed point iteration. Remember, fixed point iteration was just effectively what I'm doing Gauss-Seidel, but it was for one or two equations. And I would go ahead and guess a value of x and plug it into my equation. And so here, for example, here I've got this is a plot from the book where we've got a graph of x1 and x2. So imagine we just have a simple little matrix which only has two elements in it. It's a 2 by 2 matrix. So I'm going to take my value of x1, which initially we guess at 0. We use that to go ahead and solve for a value of x2. And then we use that value of x2 to go ahead and solve for a value of x1. And more or less, if it converged, what we would end up doing is going to the point where x1 and x2 cross, which would be the solution to that equation. But it turns out what I could do is end up with something that diverges. It's non-convergent, where again, I'm going to start off with my guess of x1, and then I go down and guess my value of x2, plug that in to get x1, and those could go ahead and diverge and get away from where the solution to that be. So that would be a non-convergent situation. And so it turns out it's really kind of related to what the slopes of these lines are in 2 dimensions, and so it would be the same thing in multiple dimensions. And there's some algebra, you can look in the textbook if you're curious, but it all comes down to the idea that the elements on the diagonal, a sub I, the absolute value of that has to be greater than the summation of everything else in the column other than itself. So it has to be what's called diagonally dominant. You need to have very, very large numbers down the diagonal and just small numbers off the diagonal. And those actually occur a lot in engineering problems. For example, let's go back to that heated bar problem. What we saw in that equation is we had a 1, 2, 1, for example. And so you've already got a value that's much larger along the diagonal, because the temperature depends the most on the temperatures close to it. So diagonally dominant is fairly common. There's one thing you can do with convergence if you think you've got a non-convergent system that helps, and it's something called relaxation. And what relaxation does is it implements this equation here where when I get my new value of x after my first guess, I would call that x sub nu, instead of using that, I'm going to go ahead and just relax it a little bit, or just kind of move a little bit toward that new value. And so I've got this value of lambda that can go anywhere from 0 to 2. It's my relaxation parameter. And so this was my previous value of x. I plugged it into the equation, got a new guess for x, and then I'm just going to go ahead and not quite move it as far to this new value. I'm going to weight it by lambda. And so I'm going to go ahead and take kind of some fraction in between that. So if lambda is from 0 to 1, what that is known as is under relaxation, because what I'm doing is I'm just kind of not quite letting it move as far as I want. I could actually take it 1 to 2, and that would be called over relaxation, because then I'm actually kind of speeding up the convergence. I see the direction it's going, and I double how far it's going to that direction. And so if I've already got a convergent system, over relaxation can make it converge faster. I have a non-convergent system, under relaxation can help make it at least a convergent system. All right, so the very last thing we're going to do is just look at how we would implement Gauss-Seidel. And so I have this equation here that is diagonally dominant. So I have 4s down the middle and 1s on the diagonal. We'll just stick with a 3 by 3 to keep it kind of simple. And so what we're going to do is we're going to go ahead and take the first equation, which would be 4 times x1 plus x2. And that right there is equal to 1. Remember, we first guessed that x2 is going to be 0. And so if I look at what that is, well, now I'm just going to have that x1 is equal to a quarter. So there's my guess. So now my vector of x is essentially a quarter, 0, 0. And then I'm going to go ahead and go down to the second equation, where I have x1 plus 4x2 plus x3. And that right there is equal to 0. And so that's this equation right there. X1 is a quarter. X3 is still a 0, everything less than that. And so I'm going to go ahead and solve for x2, and x2 is going to be equal to minus 1/4 over 4, or minus 1/16. So there's my new value of x2, and then I'm going to go to get my first guess for what x3 is. And x3, what I have is x2 plus 4x3, and that right there is equal to 4. And if I go ahead and plug that in, I'm going to get my guess, my first value for x3, and x3 is going to end up being 4 plus the 16th that came from my value of x2, and then I'm going to go ahead and divide that by 4. So I'm going to value just a little bit over 1. So now here's my new guess for my x vector, 1/4 minus 1/16, and some value a little over 1. And then I'm just going to go ahead and iterate back through and keep doing that. Notice I'm never modifying my a vector, not preconditioning that in any respect. Here's, I've just kind of printed out what the iterations are. So after my first iteration, here's my 1/4 value, my minus 1/16, and this is that value, just a little over 1. And then this is the second iteration, and then we go 3, 4, 5, so I have 5 iterations, and realize we're getting kind of close here. And so, for example, let's go ahead and look at what the error is at that. Remember, I calculated the approximate error for each one of these. And so the approximate error for x1 is at about 0.29%. Approximate error for x2, that's a little bit closer. Those are 0.14%. And x3 is almost completely converged. It's at 0.018%. Okay? So usually your stopping criterion, you're going to go ahead and look and every one of these x values has to go ahead and satisfy your stopping criterion. And so what I'm going to be doing right now, you're kind of watching your x1 value. That's the one that has the largest error. All right, so let's go ahead and review what we talked about in this video. First, we saw that banded matrices often arise in engineering problems when you discretize numerical systems. And so you have parameters that are only more or less dependent on parameters near it. And if you can do very judicious node numbering in 2- and 3-dimensional systems, you end up with fairly narrow banded matrices. We saw the Thomas algorithm. It's simply LU decomposition for a bandwidth of 3. You can make a somewhat more efficient LU decomposition by using Thomas if you know you're going to have a bandwidth of 3. That often happens in 1-dimensional problems, like the heated bar problem I showed. Cholesky decomposition has a more efficient storage mechanism because you only have to store effectively half of that matrix. And often, sometimes it naturally arises in symmetric systems. Again, that heated bar system is symmetric. The points to the left of it and right of it always have the same effect. And so you can sometimes don't even have to go through this Cholesky decomposition initial step because you've already got a matrix that is of that form. We saw that Gauss-Seidel is an iterative technique. It doesn't precondition the matrix, so we don't go ahead and do our elimination steps. And what we were doing is this is more or less an efficiency versus accuracy trade-off. We lost some efficiency, but we're going to end up with a more accurate solution because we haven't modified A overly much. And then we also saw that Gauss-Seidel convergence is guaranteed only for a diagonally dominant matrix. It can converge if it's not diagonally dominant, but if you want to make sure it's going to converge, you want to guarantee it, it needs to be diagonally dominant. And the last thing we discussed is relaxation. Relaxation can assist with convergence. And in this case, what we're going to have is an efficiency versus convergence trade-off. Since we're relaxing it, if it's an under-relaxed system, we're going to not be quite as efficient, but we're going to guarantee convergence. On the other hand, we could kind of turn that around and we could go ahead and over-relax it, lambda between 1 and 2, and we can go ahead and speed up our efficiency, and that's only going to occur if we already know that the system is convergent.